This video is about the push-pull output stage. And the whole job of an output stage is to show a low R out, which just means that if something asks for a lot of current, so if there's a lot of current output from the circuit, the output voltage doesn't get affected. So let's start with the most basic version of a push-pull output stage. A push-pull output stage, it looks like something's wrong because you're used to, coming from 307, you're used to having the N-type device on the bottom, the P-type device on top. So usually if you had an inverter, this would be a PMOS and this would be an NMOS. But with push-pull, you have the N-type device on the top and the P-type device on the bottom. That's not a mistake. Okay. Other things to notice is that this RL, it's not really part of the circuit. It's modeling it's modeling a make-believe circuit out here. So if a make-believe circuit is going to pull some current, it looks like a resistor to your push-pull stage. That's what this RL is. It's faking an input resistance of a circuit that the push-pull might be connected to. And the one thing for this lab to make it work correctly, this reference voltage right here. So you have an RL, maybe of about 1K or something. The reference voltage should be halfway between VCC and minus VCC. Let's say you use 10 volts and 0 volts, then this should be halfway between. So the reference voltage should be at 5 volts. If you're using plus 5 volts and minus 5 volts, then the reference voltage should be halfway between that, which is ground. Okay, so let's look at how this first stage works, and we'll go through the questions on my pre-lab. So the handout is posted, so if you want to follow along, just look for I think it's week 5. I think the handout's in week 5 on Canvas. Okay, so first question, if there's no current going through RL, then there's no voltage drop across RL, and V out is just the reference voltage. And for all my examples here, I'll use plus 5, minus 5. So we're looking at ground at the reference node, halfway between plus 5 and minus 5. Okay. So the reason why this first question is there is that if nothing's changing the voltage at this node sits at 0. So your first assumption on the rest of the questions in the section is to assume that this node is at 0. Okay. The second question is, if Vin equals 0 volts, how much current is going through Q3? So if Vin is 0 volts, what color should we make this? How about green? So if Vin is 0 volts, by default, we assume that this node is 0. And we go look at our transistors. And first thing you want to do is find the region of operation. So the base is 0 volts here, because Vin is 0. And the emitter is 0 volts, because our first assumption is that this node is at 0. So our VB is 0, and this is in cutoff. So when you ask how much current's going through Q3, it's 0. So I Q3 when Vn equals 0 is 0. And then same thing for Q4. The next question is Q4 conducting? So again, you want to write down the base voltage. You've got an emitter voltage of 0. So base voltage is 0, emitter voltage is 0. This is also in cutoff when Vn is at 0. So I Q4 equals 0 when Vn equals 0. Okay, let's look at next question. So that's question 1, 2, and 3. So then the next question is, if I raise Vin just a little bit more than VBE on, or some amount more than VBE on, what happens? So if Vin is Vin is VBE on plus a little bit, plus alpha. Then by default, you assume this is 0 volts. And now this is VBE on plus, so now Q3 is conducting. The next question is, if VB on is positive, VB on plus alpha is Q4 on, and you can see that it's not. This is 0, and this is a positive voltage. So actually, this is what you want is this node to be greater than this node, and so that's in cutoff. So when Q3 is conducting, Q4 is in cutoff. So for this input, okay. And the next question is if this is negative VBE on minus a little bit more, oops, not infinity. So now this is the base is for Q3, the base is a negative voltage, and you assume that 0 is kind of the default. It actually follows it when the transistor's on, it follows it. But now this VB is definitely, the base is not VB on above this node. So this is now in cutoff. So now they've switched. Before, the top was conducting and the bottom was in cutoff. But now with this, if you assume this is by default 0, and now this is negative VB on, now you have enough voltage across Q4 and it's conducting. So when Vin is 0, neither are on. When Vn is VB on above 0, then now you have VB on across base emitter of Q3, and Q3 is conducting, but Q4 is off. If you go negative VB on, now Q4 is conducting and Q3 is off. So those are, this is the first version of the circuit. Now, you can go let a dog in. So this next circuit, ignore the REs here. Assume it's like the previous circuit. Assume that there's no resistance here. We'll talk about those in a little bit. But now let's add some intermediate circuitry. So the output stage, usually have your gain stage and then your output stage. But we're putting some circuitry in between the gain stage and the output stage to put a difference of voltage on the bases of 2 VBE. And you can figure out what voltage you need across here because you want both of these just on the edge of turning on. So that means you have a VBE, let's look over here, just because the REs are getting in the way here. So it means you have a VBE across the base emitter of Q3 and a VBE on across the emitter of Q4. So notice that the emitters are at the same voltage. So if you need a VBE on across Q3, that means from this node to here, you need to have a VBE on. And then also here, from this node to here, you need a VBE on to get both of these right on the edge of conduction. This node is the same voltage. So what you do is you drop a VBE on and then you drop a second VBE on. So you actually, if you want both of these on the edge of conduction, then you need 2 VBE on between these bases. And this intermediate circuit here is a circuit that generates 2 voltages, and they are 2 VBE on apart. And the way to look at that is these are two common collectors, and another name for a common collector is a level shifter. So an NPN-based level shifter or a NMOS-based level shifter shifts the voltage down, and a PNP-based or a PMOS-based level shifter or common drain shifts your voltage up. So on a PNP, the emitter is higher than the base. On an NPN, the base is higher than the emitter. And for BJTs, which is what we're using here, that difference is about VBE on. So Q2 shifts your V in up by a VBE on, and your NPN-based common collector shifts it down by VBE on. So this wire is VB on higher than VN. This is VB on less than VN. So the difference between these two wires is 2 VBE on. Okay, so let's see how that works. Let's answer some questions there. So in this circuit, make it smaller again so it more fits. So if Vn is 0, remember the previous circuit, when Vn was 0, both Q3 and Q4 were off. So if Vn is 0, then, and this is a default of 0 volts here, this is VB on, you've got 0 volts here, this is just barely, this is just turning on. Okay, same thing down here, if this is 0 and this is negative VB on, and this is just turning on. So actually these are both conducting now. Both Q3 and Q4 have enough VBE voltage to have them both conducting. These RE resistors right here, they protect against current runaway, but in this case, they also turn down the current when they're both on. Okay. I forgot to say something important about the last circuit, so actually let's go back there and I'll make a second video to finish up this one. But on this circuit, let's look at the two cases, or the three cases here. So we had when Vin was 0, neither of the transistors were on, no current through I out, V out sitting at 0. Okay. For this one, when you have VB on plus, Q4 goes into cutoff. Let's see what that means. Q4 goes into cutoff. Q4 goes into cutoff, and it's like it goes away. So what's left is, I'll just pull out what's left. You have V in, using this. This RL becomes the bottom half of a common collector. So when Q4 is off and Q3 is on, you just have exactly a common collector. Okay. Then when you look at the other, when V in goes down minus VBE on, when Vn goes down, VBE on, now Q3 is in cutoff, so it's gone. And if you redraw the circuit, now you have V in, and you have your minus 5 volts. And then you have, there's actually ground here. And you have, once again, you have a common collector, but this one's PNP based. So what happens is, how the push-pull works is, it turns on one common collector if Vn is high, and it turns on a second common collector if Vn is low. And by putting 2 VB on between the bases, what happens is if Vn just goes up a little, then it turns on the top half. If Vn goes down just a little, not here, this doesn't have the 2 VB on between the inputs, but yeah, if you had the 2 VB on between the inputs, then the top common collector would be operating, or if Vn went below 0, then the bottom common collector would be operating, and only one is on at a time. And the reason why this circuit is good is it actually uses half the power of just using a common collector here. It's totally fine to use a common collector, but a common collector, you look at a common collector, if you look at a common collector, it goes from whatever the supply voltage is to whatever the lowest voltage is. So a common collector, this common collector right here, would always be operating with 10 volts across it. And remember, power equals IV. That V is whatever your supply voltage is. But if you use a push-pull, and a dog whining at the door. But with the push-pull, since you've picked a reference voltage that's halfway between your positive rail and your negative rail, what happens is when the top's on, instead of getting a common collector that goes from VCC to minus VCC, you get a common collector that goes from VCC to ground. Q4 goes away. Now you've got a common collector that goes to ground. And since you've picked this reference voltage, it goes from VCC to the reference voltage, or reference voltage to minus VCC. Since you only have half the voltage, when only one side's on, you only have half the voltage, either going from ground to minus VCC or VCC to ground. That means that in your power equation, your V is now VDD over 2, or whatever your reference voltage makes it. Okay. I kind of rushed and did a bad job on that, but please ask if you have. I'm going to go on to the next circuit, but might as well. It's going to go pretty quick. So it's got all the important points, that it's two common collectors that are just switching between each other. And the reason why it's advantageous is because when the top common collector is on, you're using half the voltage you would if you just used a single common collector here. But anyways, okay, so let's go through the questions real quick. Now if Vin is 0, both of these are conducting slightly, and pretty much you can think of it as the current through Q3 is going through Q4, so there's still no current out the output, so this you can still think of that as 0. If Vin is less than 0, just a little bit, then this right here is going to be a little bit less than negative VBE on, because this shifted down by VB on, and your Q4 is going to turn on, but your Q3 is going to turn off. So you've got the bottom common collector running. And if Vin's less than 0, Q3 is off, as I said. If Vin is a little bit greater than 0, now Q3, the common collector that includes Q3 will be on, but Q4 will be off now. Next question. Yeah, and I think that hopefully that gave you a good introduction. If I had more time, I would redo this video because it didn't follow the perfect story. But hopefully it gets the message across. But any questions, feel free to write me, and I'll try to clarify stuff.